All right, well, did you have a good weekend? All right. All right, we got to jump right back in. We were doing logarithms last time. And what's going on? Like the room is tilted this way. There's nobody over here.
It said 10 people that job.
Is it? I don't know. Okay. All right, well, we're going to continue logarithms. Remember from last class, we had, was it 7 properties that I gave y'all? 8 properties? No.
Oh, yeah, 7.
7 properties from last class. All right? I'm going to be using those properties now to continue this section with this example. We are asked to solve this equation for x. All right, we want to solve this for x. So here's x, right? We've got an equation. This is a logarithmic equation. So how in the world are we going to solve this for x? This looks terrible, doesn't it? Like, welcome back, right? Here you go. Well, let's try and use some properties. One of the properties that we had from last class was property, well, the 7th one. It was log base b of m raised to the p equals p log base b of m. Okay, that was a property from last class that said that if you had a power on the thing that's being plugged into the log, which we call the argument of the log, if you have a power there, that power can come out in front. That's kind of where we ended the class. Now we're looking at this, and we notice first of all that all of the logs have the same base, b, 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 b. We need that, in order to be able to combine logs together, we need them to have the same bases. So now I'm going to take this number out front, and instead of using this property where we pull the number out front, we're actually going to use this and push the number back up as a power. So I'm going to actually put this 2/3 back up as a power, this 2 as a power, and then here there's really a 1, so I'm not going to touch it. So my next line is going to read like this. Log base b of x equals log base b of 27 raised to the 2/3, and then plus log base b of 2 to the what? 2, right? 2 squared. And then minus log base b of 3. All right. Now, let's see if we can't figure out what 27 to the 2/3 is. Do y'all know what this is? No? All right, so let me put a property up here of exponents. If you have something raised to a fractional power, all right, x raised to a fraction, this is equivalent to the mth root of x to the n. Or you can do it this way. You can do the mth root of x all to the n. All right, yes?
That's x and m, right? Over m.
This is n over m, yes? N over m. You take the mth root of x to the nth power, or you can do the mth root of x and then raise that answer to the nth power. All right? This is a property of exponents. We call these rational exponents. We call this radical notation. So if I have 27 raised to the 2/3, that's equivalent to, what would it be in terms of this one? What root is it? Cube root, 3rd root of 27 squared. You can write it that way. Or, how about the other notation? It would be the cube root of 27, but then squared. Do y'all see this property being used here? Yeah. So which of these seems more reasonable to you? Do you want to square 27 and then take the cube root? Or do you want to take the cube root of 27 and then square it? Cube root of 27. Because what is the cube root of 27? What number times itself 3 times is 27? 3, right? 3 times 3 is 9. Times 3 again is 27. So the cube root of 27 is 3, yes? But then 3 squared is 9. You were giving me the final answer, I think, right? So the final result of this is 9. Understand? So I can rewrite this. Next line, I'll do it up here. So the next line becomes log base b of x equals log base b of what? 9. Okay, plus log base b of, now this one is not as difficult. 2 squared is 4, right? So 4. And then minus log base b of 3. Okay, so what I'm trying to do here, and maybe I should have alluded to this in the beginning, is on the left side of the equation I have one logarithm, right? One log right here. And on the right side I had 3 separate logs. I'd like to put those logs together into one log so that on the right side I have one log and on the left side I have one log. To do this, I first have to push these powers up. Then I can start pushing them together. So how can you redo just these first 2 logs? What can I do with those? What property from last class can I use to put those into one log? What is that? Property 5. Property 5, and I don't want to write all these down again because I did that last class. Property 5 said log base b of m times n is equal to log base b of m plus log base b of n. So if you had one log with multiplication, you could split it into 2 logs. Or the other way is if you have 2 logs with addition, you can put it into 1 log with multiplication. So I'm going to use this property this direction, from the right to the left. So what can these 2 logs become? It's a single log, right? Log base b of what? What are you going to do with the m and the n, the 9 and the 4? You're going to put them together, 9 times 4. So 36. So this is going to be log base b of 36, and I still have minus log base b of 3. Understand? Any questions? All right. Y'all are look like zombies today. I know it's Tuesday, but y'all got a free hour this weekend, right? Didn't y'all get a free hour? Didn't feel like it to me. It felt like I lost an hour. This, for some reason, didn't work the way it usually does. Okay, so that property allows us to do this. Now what? Can we put these 2 logs together? That's property 6. So if we change this to subtraction, how does the formula change over here? It's not multiplication, it's division instead. So that's property 7. Okay, so I'm going to be able to rewrite this as log base b of x equals log base b. It's going to be a single log now, okay? This is the biggest mistake I see students do. They say, okay, subtraction I can turn into division, and so they do this. That is not what the property says. It does not say that 2 logs with subtraction become 2 logs with division. It's 2 logs with subtraction become a single log with division inside of it, all right? So don't make this mistake. So I have these 2 logs with subtraction become a single log. The division inside is going to be 36 divided by 3, right? Which is 12. Okay. Any guesses on what x is? Now that we got it to this? 12. So look at why it's 12. The left side and the right side are almost identical now, right? Log, base B, x, 12, right? In order for these two to be equal, this would have to be a 12, so it would match up perfectly, wouldn't it? So at this point, we can say x is 12. And we're done. So the goal of the problem was to take that big old ugly thing, condense it down into a single log, and then get it to match the other side. And we're done. All right. You have several homework problems like that. What's that? Did you try those? You're only supposed to go through 33.
I
You
did.
did all of them? Okay. All right, let's try another one. Let's do... Let's do log, so same instructions, solve for x. Log base 10 of x plus 6 minus log base 10 of x minus 3 equals 1. All right, this problem is different than the last one in the sense that we don't have like a log on one side and then a bunch of logs on the other, and we're going to try and condense so we can make them match. It doesn't look like that, right? Do y'all see that? It does not look like that. Okay, so the best thing that we could maybe try here is to see if we can't put these two logs into a single log. All right, let's see if we can't turn that into one log. So can you put those two logs together? Yeah, they have the same base, right? They have subtraction between them. That means it's going to turn into a single log with division inside of it, right? So what's my new log? Log base b of what? 10, yes, sorry. 10, thank you. Of what? You have to do this divided by this, right? Let me write it down. I have to do x plus 6 over x plus 3. Now, I heard 2. Maybe it is. Maybe I need more sleep. Okay, x plus 6 over x minus 3. Okay, be careful here. You can't cancel these x's. All right? Can't do that because you have two terms on the bottom. The only way you could cancel is if you had multiplication between these. Then the x's would cancel. So we can't do anything with that. All right? That's the left side. What's the right side? Equals 1. Okay. All right. Well, I don't know if you think that looks better, but it's different, right? It's instead of 2 logs, we have 1 log. All right. Now, do you remember last class I told you about this thing that I called a loop? Remember that loop idea? Okay, I'd like for you to apply the loop to this equation. You start at the base, right? And you say 10, what? Raised to that should be equal to that. And let's write that down. Okay, let's write down exactly what that loop is telling you. 10 raised to the 1 must equal x plus 6 over x minus 3. Do you all agree with that? Now, 10 to the first power is 10, right? So I don't really need to do anything with that. And that is a problem that you probably got on that take-home packet in the very beginning, like, are you ready for this class? Remember that thing? This is what we call a rational equation. And how would you solve this rational equation? Can't set each one equal to 10. That's if it was multiplication, we would, even then. If we're trying to solve for x here, right? You have a rational expression, rational meaning ratio meaning fraction. what you want to do is clear the fractions. So that means you're going to multiply both sides of the equation by the denominator. Okay? So, yeah, I feel like I'm I don't know. Let me do it, see if it rings a bell here. I'm going to do x minus 3 here, and then here x minus 3. Now what is the effect of me doing that on both sides?
Cancels it.
On the right side, it's gone, right? That's why I did it. No more fraction. On the left side, I actually have to multiply this times 10, which means the 10 has to pass through to both of those. Look, this was called a rational equation. And the first step to solving a rational equation is to clear the fractions, which is what I just did. Now, what am I left with? What's the equation that I'm left with here? 10x minus 30 equals what? X plus 6. What type of equation is this?
Linear.
What type of equation is this? Linear? How do you solve linear equations? Get x by itself on one side. All right, so I'm going to choose to do my x's on the left side. So I'm going to subtract x here, subtract x here. I get 9x minus 30 equals 6. And then I'll move the 30 to the other side by adding 30. And you get 9x equals 36. And then finally you divide both sides by 9, so you get x is 4. Okay. That's how you do that one. So this logarithmic equation right here turned into a rational equation, which turned into a linear equation, which we can solve. This is why we study all types of different equations, because to do logs, you got to be able to do this. And I'm going to do another example. You'll see we're going to have to be able to do a quadratic equation. So now, I didn't do this on the previous problem, but I will point it out here. With the logarithmic equations, you have to check your answers. All right, so you see this 4 here? You have to take that 4 and you have to plug it back in. Now, when you do this, all you're looking for is what you would get in here if you plugged in 4. So what would I get if I plugged 4 in here? 10. And what do I get here? 1. Okay. The key to this is that this result cannot be negative and it can't be 0. Because anytime you have a logarithm, you can never have a negative inside. That was one of the, when we started talking about logarithms, we said what's in here cannot be negative, cannot be 0. So as long as that's a positive number, and that's a positive number, we're in business. So that's it. We are okay. We can accept this answer. I say that because on one of your homework problems, when you get the answer, if you check it, you get a negative in here, and that means it's no solution. All right? Okay, let's do one thing. I'm going to do the same problem. I'm going to start over. I'm going to do the same problem, just one small change. Instead of a minus here, I want to put a plus. How would you approach this differently now that you have a plus there instead of a minus? When you put those two together, you're going to multiply them, right? Instead of dividing them. So this is going to become a single log again, log base 10. But now you're going to do x plus 6 times x minus 3. You're going to figure out what that is, equals 1. So if I multiply those two together, you have to do like a FOIL, right? FOIL that out, and what do you get? Log base 10 x squared, what is it?
X squared minus 3x.
So here to here would be x squared. Here to here would be minus 3x. Here to here would be plus 6x, which would be plus 3x minus 18. And that equals what? 1. Okay, any ideas here on what to do?
10 to the power of 1.
Okay, so that loop thing again. Do the loop thing. The 10 to the 1 equals, all right, so let's try this. If I do 10 raised to the 1 must equal this, that means 10 must equal x squared plus 3x minus 18, like that. Now what type of equation is this?
Quadratic.
Quadratic, okay? So in the previous problem, when we had a minus here, right? When we had a minus and we did this thing, we ended with a rational equation, so we had to go solve it, right? With a plus here, I'm ending up with a quadratic equation which I need to solve. So how do I solve a quadratic equation? How are you going to solve this quadratic equation? Set it to 0. So that means subtract 10 on both sides. So this, if I subtract 10 from 18, I get negative 28. And then how would you solve that? Does that factor? I think we may have gotten lucky here. Does this factor? Is it 7 and 4? X plus 7, x minus 4? That was not intended to work that way. I got lucky. I thought for sure we were going to have to do quadratic equation, like the quadratic formula, because I just made this problem up, but it looks like it factored, right?
How did you get the 0 after 10?
Okay, so I subtracted 10 here, subtracted 10 here,
Oh,
right? So that became negative 28. And then we got lucky here. So we have two solutions, don't we? What are our two solutions? Negative 7 and 4. These are our, I should say, these are our potential solutions. We have to check these answers. So let's check them and see if they work. Let's try negative 7 right here. I have to go back to the original problem. Negative 7 plus 6 is what? Negative 1? Can't have a negative in here. Right? So it doesn't work. You can even see negative 7 here wouldn't work. Negative 7 minus 3 is negative 10. No go. So we scrap the negative 7. How about 4? 4 plus 6? 10. That's okay. 4 minus 3? 1. That's okay. So 4 is our only solution. Now, I'm going to actually plug it in because I want you to see that it is the correct solution, but this will also bring up some of the other properties from last class. If I plugged 4 in here, this would be log base 10 of what? If I put 4 here. 10. And then plus log base 10 of what? 1. Okay. So from last class, do you remember what log base 10 of 10 is? What's log base b of b? This was property,
It's itself, isn't it?
this is property 2.
Itself.
It's just 1. It's 1. Log base b of b is 1. So if I have 10 and 10 here, this is just 1, isn't it? Plus, now what's the log of, it doesn't matter what the base is. If you put 1 into a log, what's the answer? 0. Because you're saying 10 to what power is 1? 10 to the 0 is 1. So this is 0, and 1 plus 0 is 1. So it checks, right? That's what we were trying to get. Okay. All right. Let's move on. I told you logarithms would be fun. All right, when it comes to logarithms, there are two special bases when it comes to logarithms. the first one, log base b, right? That base, let me write it over here. When we were introducing the idea of logarithms, I think we put y equals x or something like that. I said that the base here had to be bigger than 0 and the base could not be equal to 1. That was the condition on the base. This number just has to be a positive number, but it can't be 1. So I could have an infinite number of bases, couldn't I? I have log base 2, log base 3, log base 4, log base 1/2, as long as it's positive and not 1. But there are two that are extremely important in mathematics, and they are the two I'm putting up here. Log base 10, and the second one is log base e. Now, I talked about e when we were talking about exponential functions. And I told you that e was a very special number, right? Okay, when we have log base 10 and log base e, these are like our two most used logarithms. Now, why do you think the base 10 is so important? Because our number system is base 10. Right? Y'all have heard that before, right? Our number system is base 10, but what does that mean? Do y'all even know what that means when we say our number system is base 10? Do y'all know what that means?
Every 10 you go up.
Every 10 you go up? Okay. It actually has to do with the fact that when you write down any number, you only have 10 numbers to choose from in terms of digits to use. So let's say I have a number. Somebody give me a number. 21. Okay. And then I'll throw that 6 on there. 216, right? If we look at this, there were 3 digits to this number, right? 2, 1, and 6. When I'm choosing this first one, I only have 10 numbers to choose from. The 10 numbers I have are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Those are the only numbers I can put here, right? 10 numbers to choose from. Then here, I get 10 numbers to choose from. This one, 10 numbers to choose from, right? Understand? So all numbers, the digits of every number, can only come from 10 possible numbers, all right? That's base 10. Now, the reason why base 10 is the base we use, does anyone know why we use base 10? Because we have 10 fingers, exactly. If we had 12 fingers, we would most likely use a base 12 system. Most likely we would have 12 digits to choose from because 10 was natural for us to count, right? Or if we only had 3 fingers on each hand, we'd probably use base 6. If we only had 1 finger on each hand, then we'd use base 2. Do you all know anything that uses base 2? Binary. Computers, your phone, right? Your phone. Like whatever you're looking up on your phone right there? Like whatever you're looking up, it's just zeros and ones. That's the only thing a computer knows. Your computer has digits, and it gets to choose from 2 things, a 0 or a 1. Now, why is it that computers work very well with zeros and ones? Why not have base 10? What's the only thing that a computer knows? No? Yes. No electricity is there, electricity is there. It either sees the signal is there, 1, or no signal, 0. That's it. That's all it knows. Ones and zeros, ones and zeros. That's it. Signal, no signal. So your computer, our phones, everything you use that's digital, right, is just a bunch of zeros and ones. That's all it is. So if you've ever seen like the Matrix, they have like this, zeros and ones going everywhere and all that. It's because that's the way a computer operates. We use base 10 because we have 10 fingers and that's what makes most sense to us. All right? So when you have a logarithm base 10, it's the one we like, right? It's the system we like. We like base 10 systems. Do y'all know of any other base systems that are used? You knew binary. Do you know any other? There's hexadecimal. Anyway, there's number systems out there that have like 16 things to choose from. So they use 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and when they get past that, they use letters. A, B, C, D, and so they have, you can have a number in a different system that looks like this. Maybe it has 4 digits. Maybe it's like B7C9. And that is a number, but it doesn't look like a number. It's because it's in a different system. Okay, I'm going off topic.
Is that like the license plates where they have them?
No, license plates, I mean, that's a little different. It's kind of like, no, it's very different. I don't want to get too much into it. I mean, do y'all really want to know? I mean, no, you're just going to try and get me off track. Most people don't understand what digits mean anyway. Like when you write down 216, like what does this mean? 6 ones, 110, 200s, right? Okay, so if you write down in binary 110, what does that mean in binary? Yes, it does, but if the 6 here means 6 ones, and the 1 here means 110, and this one means 100, then in binary, what does the computer think this is? 0 ones, 1 2, and 1 4. What? Okay, now I'm going to get too far off track, and it's not relevant to this class. Okay. All right. So now, log base 10 is an important one. We use it because it's our base for our number system. Log base e is important because that e was that number that we had looked for and we found it, and it just appears in nature all over the place, and it works. So these two are the most important ones. And so since they're so important, we don't write them log base 10 and log base e. We have a different notation for them. If you want to use log base 10, all you have to write is log, and everyone understands that the 10 is there. It's kind of like when I write the square root of 4 and I write the cube root of 8. When I write cube root of 8, I have to put the 3 out here, right? But when I put square root of 4, I don't put the 2 out here, do I? But it's understood it's there? So it's the same thing. When you write log, L-O-G, everyone needs to understand that the base is 10. All right? Now, this one, we can't use log because we already used log, so we have a different notation for this one. It's L, that's an L, not an I, and then N, ln, which is what we call the natural log. So why don't they call it NL for natural log, right? Because the French, they say things, they would say that logarithmic and natural or something like that. Logarithm natural. So natural log is written ln. You have a key, you have on your calculator a key for both of these. And they're different keys. You can't, if you want to do this, you can't use this key. And if you want to use this, do this, you can't use this key. So I asked everyone to bring their calculators, right? I'm sure you all did. Yes? All right, so next class, if I see anyone without a calculator, I'm going to give a quiz on the spot for a calculator, and you'll get a 0, okay? Next class, it's a free 100 if you bring your calculator, but if I see like 3 or 4 people without calculators, now I don't mean phones, I mean real calculators. Why not today? So you want to help some of your classmates get zeros right now? Yeah?
Yeah, every man for himself.
I like that attitude. I like that attitude. Okay. Well,
Life is, though. You never know.
it is, right? No one cares about you.
I think we should catch him on the day he does not.
Yeah. All right. So please bring your calculator because I can sit up here and I can do these problems and give you answers, but you need to be able to do it yourself. And on a test, you don't want that to be the first time you broke your calculator out, right? It happens all the time. But okay, so let's see if we can't go kind of back to some problems that we were trying to solve before. Well, let's just make sure you can use your calculator. Let's try, what is log 4? So you need your calculator for this. What is this really asking? Can somebody tell me what this question is really asking?
Log 10 base
10 raised to what power? 10 raised to what power is 4? That's what that's asking you, right? Because the base is 10, even though I don't write it. 10 to what power is 4? Well, I don't know, but your calculator will. What is it? What do you get? 0.6 something? Everyone get 0.6 something? So the answer to this is 0.6. 0.6 what? 0? Okay. 0.2, whatever. All right. So that means if you take 10 and you raise it to the 0.602, try that. Try 10 raised to the 0.602. You should get a number really close to 10. It might be off a little bit because we're going to have some rounding error here. But do you get something close? You know how to raise that? Every calculator is different. So 3.98. Okay, so close. The more decimals you go out here, the better your answer is going to be. All right, good. Now, let's see the difference between that and the natural log of 4. So what is the question that this is asking? This was asking 10 to what power was 4? This is asking e to what power is 4? That's what that's asking. And the calculator says? 0.439?
1.38.
Oh, 1 point. Yeah, that's right. 1.38. Close enough? 1.38. So if you took e and raised it to the 1.38, you should get something pretty close to 4. All right? Now, I want to revisit a question that we did when we first started doing this log stuff. Let me just ask you this. Do you know what 5 to the x equals 7 is? Do you know what x needs to be? Do you know what we raise 5 to in order to get 7? You don't, right? I mean, it's not obvious. Like if this was 25 over here, if this was 5 to the x was 25, could you tell me? Right, it would be 2. But if it's something like this, it's not a nice number that goes in here. How do we solve this, right? We don't really know how to do this until we provide you with what's called the change of base formula. All right, so here it is. Change of base formula. This is a very important formula. All right, here's what it says. It says log base b of m equals natural log of m over natural log of b. All right, this is a very, very powerful and useful formula. I did not give that formula to you last class, so this is the first time you're seeing it. All right, let's go back to this example, 5 to the x is 7, okay? That is in what we called exponential form. Last class, I was teaching you how to convert from exponential form to logarithmic form. Could you convert that to logarithmic form for me right now? It's log, and then what's the base? 5, and then what goes here? 7, and then equals x. See, what's nice about the conversion from exponential to log form is that I wanted to know what x was here, right? But this now is telling me x is equal to that, right? Now, your calculator has 2 keys on it, the log key and the natural log key. It does not have a log base 5 key on it. Well, some of them do, but most of them don't. You don't have a log base 5 key. And the reason you don't have a log base 5 key is because of this formula. This formula says if you have any log of any base of anything, you can turn it into natural log of that m divided by natural log of the b, which means you only need the natural log key on your calculator to do any logarithm. That's why your calculators usually only have the natural log and then the log buttons. So how can I use the change of base formula to rewrite that? Using that formula. I do ln 7 over ln 5. That's equal to x. You need to be able to do that on your calculator now. So try and do, this is two different natural logs, right? It's not a single log, it's two different logs. So try natural log of 7 over natural, I actually brought my calculator. Didn't I? I brought a calculator. Yes, it is. 1.209 is x. Does that answer make sense? If you take 5, what would be 5 to the first power? 5. 5 squared would be 25. It's too much, right? So the answer here has got to be between 1 and 2. So, all right. We're almost done. How many years will it take to turn $10,000 into $15,000 if invested at 6% interest compounded monthly? We're going to use which equation? Is it the PERT?
Yes.
There were two formulas, right?
Yes, because it's compounded.
The PERT is only used when you compound what? Continuously. This one's compounded monthly. So we're going to use the other formula. So the other formula that we had was A was P, parentheses 1 plus R over N raised to the N times T. So look at this information. This is different than any problem we've done in the past. Normally, like on the test, I said, hey, you got this money, you put it in the bank for 5 years at this interest rate, how much will you have at the end, right? This is different. This is saying, hey, look, I want to put money in, I want to turn it into this at this percentage. How long is that going to take me, right? How long is that going to take? How long does my money need to sit there? So let's try and figure out the pieces here. How many years is T, isn't it? That's what we want to find? T? 0.5? You already got it? Okay, we'll see. We'll check it. I don't know. Doesn't seem right, but we'll see. All right, so what about 10,000? What's 10,000? That's P. That's the amount that you're going to start with. What is 15,000? The amount that you want at the end, right? That's A. What is 6%? That's your R, but remember you have to turn it into a decimal. And then what about compounded monthly? What does that mean? N is 12. So let me go fill in all this equation here. I have 15,000 equals 10,000. 1 plus 0.06 over 12 to the 12t. Now, when we started talking about logarithms, I put a problem like this up on the board. And I said, our goal is to be able to do something like this. And I said, the problem that we have is that the variable we're trying to solve for is up in the exponent, and we have to be able to get it down from there. The only way to get that down from there is to rewrite that from exponential form to logarithmic form. But we didn't know what a logarithm was at that point. So we're about to do that, but there's one problem that we have to address first. We must get this 10,000 out of here. That way we have something to a power. Right now that 10,000's got to get to the other side somehow so that we have just this to this. So this is multiplication, divide. Divide both sides by 10,000. And you should get 1.5 equals 1 plus 0.06 over 12 to the 12t. All right, so I divide both sides by 10,000, I get 1.5. Is that okay? Let's go ahead and figure out what this is. What is this? 0.06 divided by 12 plus 1. And let's go and use as many decimals as we can here. 1.005. So we have 1.5 equals 1.005 to the 12t. Now, if you squint your eyes hard enough at this, if you squint your eyes at that, I want you to realize that what you're looking at right there looks a lot like the problem we just did. We have a number to a power equals a number, right? And we're trying to find out what this power is. We have a number to a power equals a number, and we're trying to figure out what this power is. Understand? So I'm going to go from here to logarithmic form. What is the logarithmic form of that equation there? I'm going to have log base what? 1.005, okay? That's my base. And then what goes in the log? 1.5 equals what though? Be careful here. 12t. The whole thing, 12t. All right, now whenever you go from exponential to log form, I always recommend that you just double check it with the loop. This says 1 raised to this equals that, right? I'm sorry, 1.005 to the 12t, that's what we have here, equals 1.5, which is this. So I have written it down correctly. Now, what does the left side, bless you, what does the left side become? You don't have a log 1.005 key on your calculator, right? So you're going to do that changing of base formula. You're going to make this natural log of something over natural log of something. What are those two somethings there? What goes here? It's one of these, right? 1.5. You can kind of remember it because this 1.5 is like above that one. So this one goes on top, that one goes on bottom. 1.005. And then that must equal 12t. So still put 12t on this side. And then get your calculator out and do the left-hand side. So natural log of 1.5 divided by natural log of 1.005. 81.29 is what I'm getting. So 81.29 equals 12t, right? Finally, solve for t. So divide both sides by 12. 6.77-ish equals t. So how long is it going to take to turn 10,000 into 15,000 if it's invested at 6% and compounded monthly? Almost 7 years. Almost 7 years.
So for the L,
ln?
solve that step, how did you get, well, how do you know?
You have to know that this right here, the only way to compute this is to use that formula. Okay, how about this problem if I changed it to, instead of compounded monthly, compounded continuously? Same problem. What would change? This would change, right? And it would change to PERT, right? Like this. That's what it would look like. And then you would have 15,000 equals 10,000 e to the 0.06 t. Right? That would be the new equation if I change the problem from monthly compounded to continuous compounded. We still have to solve for t though, right? So what would be my first step? Divide by 10,000. That's going to be the same. 1.5 equals e to the 0.06 t. And now, this part's kind of interesting because I'm curious to know what you're going to do here. Rewrite this as from exponential form to log form, right? So when I do that, I get log base what? E, and then what goes here? 1.5 equals 0.06 t. Yeah, so this is the part that I'm curious to see how you handle this. Because you could use the same formula we just used, the change of base formula, right? And do natural log over natural log. However, what does log base E really mean? That's natural log, right? So isn't this really just saying natural log of 1.5? Isn't that what that really means? Yes. Now, what if you didn't do that? And you said, no, I'm going to use that formula. You would do natural log of 1.5 over what? Natural log of E. Right? And if you do this on your calculator, natural log of E, you're going to get 1. And so it just turns into natural log of 1.5. So I prefer that if you see this log base E, that you know that it's natural log and just turn it from here to here. To get this? Well, I did the backwards of the loop. This is what we call exponential form. I converted it to logarithmic form. I can check myself by doing the loop. E to this should equal that. That's what this equation is saying, right? E to the 0.06 t is equal to the 1.5. All right, so on your calculator, do natural log of 1.5. .405, something like that. Equals 0.06 t, right? And now divide both sides by 0.06. And you get 6.75. What was our answer previously? 6.77. Really, really close to the same answer, right? All right, what time we got? We have about 20 minutes. I want everyone to spread out, to go to a computer, spread out like a testing environment. I'm going to give an in-class quiz over what we did today. You can use your notes. You may not use each other. Okay? So spread it out, grab your books.
You grading that too? Or?
What's that?
You grading it?
I am going to grade it, yes. All right. No working together. It's okay if you're on the same table. Just yeah. I think we can make this happen. Someone here? All right, so I'm going to put up the problems on the board. You can do this on a separate sheet of paper that you're going to turn in. So don't write it on the back of your notes or any back of something. Make sure you put your name. Make sure you put today's date, which I believe is the 7th, 6th, 7th? Okay. All right, first one. Solve for x. Log base b of x equals 3/2 log base b of 4 minus 2/3. Oh, you know what? I apologize. I'm going to change this. I'm going to make it so you don't have fractions. It'll make it a little easier for you. Log base b of x is log 3 log base b of 2 plus 1/2 log base b of 25 minus log base b of 20. So, that's number 1. Number 2. Same thing, solve. Log base 10 of x plus log base 10 of x plus 1 equals log base 10 of 6. 3. Okay, last one is you want to turn $35,000 into $50,000 at 4.75% compounded continuously. How long? All right, those are 3 problems exactly like what I just did in class today. So here's the reason I'm doing this. If I go over something today and you're just kind of here and kind of not really paying attention, if you can't retain this 5 minutes after I go over it, then it's going to be difficult for you to retain it at home, right? So you need to be working on, in class, focusing on what's happening and not thinking it's going to happen, you know, some miracle at home later, or the tutoring lab, you're going to go learn it all. This is where it should happen. And if you took good notes, you've got a template for how to do each of those problems. All right, you have till the end of class. See how much you can get done. Does everyone understand number 3?